This new section is entitled Independent Random Variables. The This is one way of showing equal sign, you have independent. Now, in terms, you can also show, so I'm just going to leave it at the in terms of the joint distribution combinations of AB. And yet another one, if X and Y are random, and again, this is for all Y pairs. So you have four ways of verifying independence. Some, though, are for continuous, and some continuous random variables, and others are for discrete random. Or X and Y independent. Okay. Now, independent N plus N independent trials, probability of success is P, are performed. First in trials, S is in the M trials. First. X and Y are obviously independent because we are performing a number, N plus M, independent trials. For example, if in the first, let N be 15 and M be 11. If in the first 15 trials you have this, are independent. You can't tell me any new information about the number of successes in the last M. It can be anywhere between 0 and 11. If you toss a coin 26 times, and for some reason you want to isolate the first 15 tosses and the last 11 tosses, and success is the head. If you get 14 heads, it's not going to influence on the first 15. You got 14 heads. It's not going to have any effect on the last 11. It's not going to have any else. That was given. Okay, so clearly X and Y are independent. But we need to prove it. We need to prove it. The probability that X has Y the probability X normally we write a comma. Well, this is binomial. Either you have a success or you don't have a success. The probability in the first n trials, because X came from the first n trial, you have I successes. I, P to the I successes. Failure will be n minus and Y successes. J successes on the last M trials. So from the last M, you just have J successes, P to the J, Q to the M minus J. And I ran out of space, but X is between 0 and N, and Y is between 0 and M. Thing is, this here is nothing more than the probability that X is I times this is nothing more than the probability that Y. That is just copying the left side. That is, this probability is equal to this probability. But by definition of independence, these are independent. X and Y are independent, just by the very definition. Now, here's the next question. How about number of independent? Okay, one should pause the tape and think about it. The answer is no. Because, let me get X in the first n trial. That is, first n, you had M anywhere from 0 to M. And when you add 0, we know that Z must be between 0 . We had, and M can be anywhere between 0 and m. When you add these, you get between 7 and m plus 7. So we learned something about v. If x is 0, v must be 0 or more. If x is 7, then v is 7 or more. You can argue, so we learned something. Different x's affect v's. If you wanted to say if x is 0, then v must be less than m. If x is 7, then v must be less than or equal to m plus 7. That is, if x is 7, v can be more than m. Can be up to 7 more. Does it have to? No. Knowing x influences z. Just like if you use z, it can influence x. For example, if v was r, which is less than n, what can you tell me about x? It can't be more than r. It can't be more than r. Just couldn't happen. Okay. So knowing z gives you some information about x. Knowing what x is z. But I put more that I just erased. And if you just in addition stated something about x influences z, or knowing something about z influences x, that would be enough to show that dependent. On a given day, is a Poisson distribution with x. Is P. The probability that a man enters the store we call Q. Is the store. Let x equal. So let x equal store and y of the store. Now we want to prove that x and y are independent. The probability that x is y now think of this for a moment as A, think of this as B, and it's in probability of A and B divided by the probability of B. Is a base that. Okay. Well, that's exactly what I want to do now. Okay, well, we're going to use that in a moment. But also remember that A is the same as A intersect B or A intersect not B. Okay. The probability of A is the probability, Well, actually, I don't want to say that. It's true, but I don't want to say it. The probability of A given B plus the probability of A given not B. The chances that you have A can be partitioned into two pieces. You have B or you don't have B. Okay, you have B or you don't have B. So, to this, probability that X equals I, Y equals J, given that X plus Y is I plus J, plus, well, if X plus Y not I plus J, well then, X plus Y is not I plus J. Okay. Let's get rid of this on the bottom. Now, this probability. If when known, given that X plus Y is not I plus J. If I is 7 and J is 4. We are given that X plus Y is not 11. Well then, what are the chances that X will be 7 and J will be 4? The answer is 0. Remember, X plus Y represents the number of people that came to the store. If it's not 7 plus 4, if it's not 11, if 11 people did not come in the store, that is what you're given. Somebody tells you, you're the boss and you come into the store and you say to your worker, how many people came in? And they say, well, I really don't know, except that it's not 11 people. 11 people did not come in. So you as the boss, all you know is you're given that 11 people did not come in the store. So what is the chances that 7 men and 4 women came in? 0. That's 11 people. There's no chance that 11 people came in, given that 11 people did not come in. This last probability is 0. And adding 0 doesn't contribute anything. So, we got this identity. And I did make one. The probability of A that is 0. To multiply by probability of that. But of course, 0 times some number between 0 and 1, because all probabilities between 0 and 1. 0 times between 0 and 1 is 0. So I can erase this. Okay. And call this if people this, so the probability that X is up equation 2. The variable. See, when you add two random variables, divide them, multiply them, the result is a random variable. X plus Y is a random. And it's a distribution. That's just definition of percent. Okay, so that's equation number 2. Remember, people like now, if they're so that's true. Now, if I put a given that, and the given that doesn't give any new information, it still equals itself. Now, if I men came in and J women came in, then I plus J people came in. So I'm just going to be redundant and say that. So the given that didn't give any new information, it's still a probability that X is I and Y is J. So the probability that X is I from the I plus J people, we want to choose I, and the probability of success, that is being a man, is I, and the probability of not success, I don't want to say failure, the women will go crazy, will be our J. So I want to substitute equation 3, equation 1. So to this. That is exactly equation 2. Times probability that X plus Y equals I plus J. One moment, please. Times the probability that X plus Y is I plus J. That's the exact probability. That doesn't contribute anything. It's just this here times I plus J, choose I, times P to the I, Q to the J. Now we in time in, we have e to the negative J Now this piece I plus j minus I factorial in the bottom. I plus j, if you take away I, you just have j. Times p to the I, q to the j. First thing I'll say, I, so we have e to the negative lambda I'm going to keep the e to the negative lambda here. Then I'm going to write the i's together. Lambda to the I times p to the I. That's lambda p to the I. Lambda to the j times q to the j. Well, that's just lambda q to the j. All over I factorial, a factorial. I put it there. Okay. No. Lambda, getting this. P's and lambda q's. The bracket, I'm going to factor out lambda. This is lambda times 1. I factored out lambda and lambda. So what's left over is literally what's left over. A 1, a minus, and a p. For 1 minus p is q. So it's lambda p plus lambda q. That's what lambda is. Lambda is lambda p plus lambda q. So lambda is lambda p plus lambda q. But that's the same as e to the negative lambda p times e to the negative lambda q. Because when you add those two exponents and factor out the minus sign, you get lambda p plus lambda q. Okay, so we have lambda p, everything but this for a moment. Lambda p to the I e to the negative lambda. Then this wanted to show that the probability equals I and y equals j is equal to equaling. What is it? X equals I times the probability that y equals j. So x and y. Somehow lambda and lambda times q. Out that q gives you what you need. Else it is true. Two people, a man and a woman, they plan on meeting at a restaurant. A form. Okay, so a man and a woman are going to meet at a restaurant. And they're going to arrive at a time uniformly distributed between 5 and 6. Okay? Now, here. Now, these two random variables are independent. Why? Because we're told how they're determined. This, they're both a uniformly distributed random variable. That is, the man is equally as likely to arrive at 5 o'clock as 5:10 as compared to 5:22 and 11.3 seconds. The same probability as arriving at 5:58 and 14 seconds. Same with Y. The woman will arrive, the probability the woman arrives at any given time between 5 and 6 are all going to be equal. The probability that she arrives at 5:11 is equal to the probability that she arrives at 5:29. They're all equally likely. Because they're independent. One's not affecting the other. The distribution is given. It's uniformly distributed. Okay. Now, we want to find the probability. We want to find the probability that the first person equal to at least 10 minutes. So X, Y are random variables. Or independent. So now pose Y larger number. X will be 15 late. Sorry, will come at 5:15. Y will wait at 10 minutes. This difference must be bigger than 10. After 5 and X comes 2 minutes minus 2, which is 13, is bigger than 10. So basically, we want the probability of Y minus X is bigger than 10. If I if I bring the y to the other side, we get the probability that y plus 10 is less than x, plus, in the x, we get the probability that y is, I could have said the same thing here. Y plus 10 is one reason, and that's because x is bigger than that is, but equal to one another. The probability, what I'm saying is, these two probabilities, the probability that x waits at least 10 minutes is the same chances that y waited at least 10 minutes. That is, these two are the same. And if you add the same thing to itself 2 times, you get 2 times this same thing. And I'll denote the same thing as that one. The probability that x is bigger than y plus 10. Now this means that x minus y is more than 10. First, and x came last. First, okay. Equal to 2 times probability. That probability is a double integral. But x and y are independent. That is, this is nothing more than fx of x times fy of y, dx, dy. Okay. First I see dx, so that must be the limits for x. Now, x came second. X came second. The least amount that x could have come after 5 o'clock is 10 minutes. That's the least it could have come. If y came at exactly 5 o'clock, yeah, x could have come 5:10, or 5:20, or 5:30. Now, what's the upper limit? Well, whatever y is, x had to be at least 10 less. It goes from, x can go from 10 all the way to y minus 10. Now, what does y go from? Actually, something's wrong there. Something is disturbing me here. I want to use this one instead. I want to use that one instead. Y is bigger than x plus 10. That means that y minus x is at least 10. So x came first. X came first. Now, x came first. So x could have come at exactly 5 o'clock. Now, y, what's the upper limit for x? It had to come at least 10 minutes before y. Hence, y minus 10. Now, the second limit, the y limits. What can y go from? Well, y had to come at least 10 minutes after x. So y had to come at least 5:10. It could have come as late as 5:60, also known as 6 o'clock. So those are the limits. And now we need to talk about what fx and fy is. Since they distribute, any given time is 1 over 6. Because it's 1 over the end minus the beginning. They each can come 60. This is fx, which is the same as fy. It's 160. It's uniformly distributed. So the probability that they come at is 60. I don't even have to tell you the time. Unless I say at 6:07. And then you say 0. They came 67 minutes late. That the man came 67 minutes late, 0. So you have 2 times. This is 1 over can factor it. 1 over 2 goes in. 0 to y minus 10, 10 to 60. The numerator is 1 for this number. 30 times 60 is 1800. This antiderivative is just x. The integral of dx is x. You plug this in, you get y minus 10. You plug that in, you get 0. The difference is y minus 10 dy. Let me erase up here. Very quickly begin that. Ten to 6. Alright. 60 squared is 30. And 10 squared. Okay. This do some array. That'll be the end of. We have 1 over 1800. This number is times. First thing I would do is divide by 10. Then, and I get 1 times 125 divided by 180. The next thing I'll do is say 5 goes in there 25 times, and 5 goes in there 36 times, and there is your answer. 25 over 36 times. 25 out of 36 times. Somebody will wait 10 minutes or more than 10 minutes. Suppose this density function and it's 0. So R, X and Y are X and Y independent. Now, there is this theorem that will eat through this problem. X and Y are independent the product h of x times g of y. Okay. Now, f x y equal to 6e to the negative 2x e to the negative 3. Clearly, I can write it as a function of x, say that function of x, times this function of y. Of course, I could have put the 6 into this function. The product, the way you multiply those three factors is up to you. It's 6 times e to the negative 2x times e to the negative 3y. I could have put the 6 anywhere. Okay. So I was able to write it as it being the joint probability density function as a function of x times a function of y. But that's not enough. The random variables have to be continuous. Well, yeah, they're continuous. So, yeah, the answer is a quick yes. Of course, you could have, and also, even 0. 0 is a function of x times a function of y. What's the function of x? 0. What's the function of y? 0. Here, that's the function of x, and that's the function of y. To be a function of x means the only letters you can see are x's. Notice I don't say the only letters you must see are x's. You can only see x's. Well, yeah. You can, okay, let me say it differently. You can see letters other than x to be a function of x. To be a function of y, you can see letters other than y. Yes, this is a function of x. You know why? When I look here, I don't see letters other than x. I don't see letters different from x. Over here, that's a function of y. Why? Because I don't see letters other than y. Fair enough, I don't see any letters, but I don't see letters different than y. So, yeah, the answer is, are they independent? Yes. Nice and quick solution. Okay, that completes the section on independent variables.